Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm John Calhoun, creator of Go for Sizes and several other Go courses. I also have the pleasure of co-hosting the Go Time podcast with today's speaker, Johnny Boursiquot. I will be moderating the talk today. For those of you who are unfamiliar with ACM or what it has to offer, here is a bit more information on the screen. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM learning resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in the professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to mention a few housekeeping items. These are shown on the screen in front of you. If you have questions at any time, please type them into the Q&A and hit submit. I'm going to be organizing questions as we go, and I will try to get to as many questions as possible. I'll also try to ask questions as we go along where they make sense, so you don't have to hold your questions till the end. This session is being recorded, and it will be archived. You'll receive an automatic email notification when it becomes available. You can also check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open up. Please take a minute to fill it out so it helped us improve these tech talks. You may also open the link to the survey at any time from the resources window. Today's presentation is The Art of Concurrency in Go. It is given by Johnny Boursiquot, or as we lovingly call him on Go Time, Go Lang Johnny. Johnny Boursiquot is a multidisciplined software engineer with over 2 decades of experience and a love for teaching and community building. He stays busy as a trainer, a speaker, a diversity advocate within the Go programming language community, where he also frequently serves as a podcast host, a user group organizer, and conference program committee member. Johnny's work appears on several publishing platforms, including O'Reilly and Packt. He has most recently been a contributing author to the book 97 Things Every SRE Should Know. He spends his daytime hours working as a Platform Observability Engineer at Salesforce's Heroku. In short, Johnny is awesome, and we're lucky to have him here in the Go community. Johnny, without further ado, take it away.
Thank you so much for such a nice intro, John. So in case you missed it, John and I actually, we co-host a podcast together at Go Time. So if after this, I've done a good enough job of getting you excited about Go, definitely do check out Go Time. We usually record every week, every Tuesday, was it? At 3 Eastern. And we have a darn good time doing it. And we love inviting you folks to the Go community. And that is one of the ways we do so. All right. So before we get into the topic at hand, I have let's set some ground rules, right? I have 3 objectives here in giving this talk. The first one, right, is to get you to try Go if you've been curious, right, and have been wondering, okay, should I try it? Should I learn it? I've been hearing things about it. It's been around for a while now. Is now a good time to get in, right? The second, right, is to give you a feel for working with the language and syntax and its idioms, right? To get you to sort of think through, okay, well, how might I approach certain kinds of problems? What ways do I have to change my thinking or behavior when it comes to solving problems with this new language? Like, how should I approach this, right? I hope to give you that kind of feeling throughout the exercises we're going to be looking at. And I also want to give you a starting point, right, on your learning journey if you decide that, okay, Go is for me, and I want to dive a little deeper, right? I have a list, right, I've prepared for you to set you on your way, because there's a lot of material out there, certainly more so than when I first started a few years ago. So if you were thinking, okay, well, where do I start? There's just so much out there. I've got a list for you that should get you on your way. Okay, so my presentation style is going to be very much like you're in a classroom with me and I'm teaching you, right? So yes, there are no slides. I tend not to do slideware. I prefer to show, right? I prefer to dive into the code with you, right? I'm going to make some assumptions about sort of your ability to follow along with me, right? John is going to serve as my sort of audience surrogate, if you will. So John's going to be sort of interacting with me as we do this talk. He's going to be asking questions, putting himself in your shoes as sort of somebody who's interested in learning more about Go, and asking sort of leading questions so that we can dive into certain areas that, based on your questions and what you're posting in the Q&A, right? He's going to guide sort of which way I go, right? Because there's a lot of material to cover, and we could spend, in 45 minutes or less is not going to be enough to cover everything. So I'm going to rely on him to sort of guide a little bit, right? Which direction we go, right? And that's going to be based on your questions. So I'm going to be answering questions as we go. So don't feel like you have to wait until the end for a separate section for Q&A. Just you put them in a chat as we go, and John will be sure to sort of synthesize those for me and sort of ask those questions as we go, and I'll be answering them as we go. All right. So my approach is going to be to sort of ease you in, right, into the world of Go, right? We're going to be building a program together, and we're going to be adding some sophistication to it as we go. So if you've never, seen Go syntax, or you're familiar but not too familiar, and you're still sort of learning, have no fear. We're going to ease in, and we're going to be adding some sophistication as we go, so you can actually see a program evolve to take advantage of the subject matter at hand, which is concurrency in Go. All right. So again, we're going to be explaining concepts as we go, and I'm going to be expecting questions as throughout the whole session as well. Okay. So some assumptions I'm making about you, my audience, is that you're familiar with the concept of concurrency, right? You're familiar with the concept of parallelism, right? You have some. I'm assuming that you have some programming experience, perhaps from other languages, right? But because of that, there are some concepts that I'm not going to linger too much on, right? I'm just going to be focusing on how do we do these things in the world of Go, right? I'm not going to explain some basic programming concepts, for example. Okay. All right. Now that we've set the groundwork, John, I was thinking one of the best ways to sort of introduce folks both to the Go language, its syntax, and sort of its idioms, and also to sort of incrementally sort of introduce the concept of how you do concurrency in Go, was that we could actually build a port scanner together. How does that sound to you?
Sounds great. First, the question I would have is, what is a port scanner?
Yes, I'm glad you asked, because so when you have a client and typical client server communication, right, where a client could be your laptop talking to a server online, it could be a server talking to another server. Whenever you have this sort of a communication that needs to take place, there's usually a handshake process that occurs between the client and the server, right, before data can start to be exchanged. So typically, the client sends a request, a reset packet to a server. If the server chooses to respond to that initiation, then it may return an acknowledgement, right? And once the client then receives the acknowledgement from the server, it sends back an acknowledgement to the acknowledgement, right? And then at that point, once that handshake process, that back and forth happens, right, then the client and the server can then start to engage in actually sharing the information across the wire, so to speak, right? So and that whole exchange can actually be done, and Go is actually very good at facilitating these kinds of network programs. It's very good at helping you build these kinds of applications, because the standard library that comes with Go has the tooling necessary to actually provide an abstraction layer on top of all that sort of interaction for you. So one of the standard library packages we're going to be using to do this work today is the net package within the Go standard library. Okay, so what I'm gonna do is actually we're gonna be going through an iterative process of actually building sort of a port scanner together, whereby both our client and our server are gonna be our local machine, but there's nothing that prevents you from actually using the same code to interact with a remote server. Perhaps if you are adventurous, you can spin up an EC2 instance or something on Amazon and basically open a particular port and have that interaction there as well. But for our purposes, we're going to be using our local machine to do the interaction between our client and server, right? But the idea is that whenever you communicate to a host, you need to specify a port that you're going to be that you wish to exchange information on. And again, if the host is willing to exchange and allow this exchange to happen, in particular, if there is some sort of process, a daemon or whatnot, that is bound to that particular port on the host, right, then that connection can happen, that exchange that can be facilitated, and data can flow back and forth, right? So now let's go start diving into some code. I'm going to share my screen now. Let's click the right button.
If you do that, Johnny, is this code the one that's at github.com/jboursiquot/portscan?
That is the one, yes. That is indeed the one. And thank you for mentioning that. All right.
Yan, if you can type that in chat.
Oh, I can also drop that in. I have the link handy. I'm gonna paste it. Oh, there you go.
So I put it in our team chat. I just don't know if that's in the chat for everybody.
Jan's got it covered. Cool. Awesome. All right. So I see that you see my my VS Code editor. All right, cool. So here we are. We're going to start out with the simplest thing that could possibly work, right? So I am going to pull up the very first thing here. And we're going to be covering some basic concepts about Go as we go as well. So again, this is sort of a dual purpose talk whereby both I'm introducing you to the Go language if this is your sort of first time coming across it, but also trying to do the job of introducing concurrency as we go, right? But this program right here, our starting point, let me bump up the size to make sure it's legible for everybody. So very, very quickly, some fundamentals here. So Go code is typically organized in what are called packages, right? So there's two types of Go programs you can actually build. One is an executable meant to be built and produced and run on a particular, in a given environment, whether you containerize it or whether you run it directly on your virtual machine, whatever the case may be, you're producing an executable, a program that you're actually going to invoke and actually run to perform a particular action. The other kind of program you can build in Go is what's called a library, okay? And those libraries are typically imported in and used within those programs that you make executables out of. And when you import those packages, there's two types of packages you can import. There's those that are part of the standard library, as we have here, right? So you see, I imported a FUMPT package. Yes, it's FUMPT, not FMT. There's the log package and the net package we're going to get into in a moment here. You can also import third-party dependencies, right? Those are going to have a slightly different sort of a name to them. They will have a sort of fully qualified path, right, to perhaps a GitHub repository, a GitLab, or Bitbucket, whatever you choose to use. Perhaps it could be something internal to your own environment. If you have your own sort of an inside the firewall kind of repository you want to pull in. Wherever those things are coming in, you can import those third-party packages, and the Go toolchain is going to make sure to actually download those packages for you if they're not present already in your local workspace, okay? But for our purposes here, everything we're going to do is going to be leveraging the standard library, so that means you don't need any third-party library and code to do any of the things that we're going to go through today. Okay, so importing those packages basically just looks like this, right? You have import sort of a block here, and we specified those packages that we are going to be using. One of the things about the Go language is that it will not allow you to leave, say, a package in here without actually using it. The same way it will not let you create a variable that you're not using in your program. So whenever you have sort of excess stuff that perhaps you might be able to get away with in some other languages, the compiler will sort of say, hey, you've declared a variable that you're not using, or you've declared an import that you're not using, right? So moving on to the sort of the entry point into our program, So again, this is an executable. Okay, we're going to be building and running this program. All right, we have package main, right, and function main as the entry point to our Go program. Okay, so basically this is a dead giveaway that you are building an executable. You have a package main, you have a function main. When your program starts, function main becomes your entry point. And if you've done C programming, these are going to be very, very familiar concept to you. Okay. So the first thing I'm doing here is declaring a variable, right? A local variable called P, right? And it's local to this block, right? And basically I'm assigning it the integer 5,000. Okay. So this represents basically the port that I'm gonna try and interrogate to see, okay, well, can my program communicate to a host, right, on this particular port? Okay, I've hard-coded that for now, but as our program goes on, we're gonna get some more sophistication. We're gonna parameterize these things, and you're gonna get to see how you can sort of have a more flexible program as we go. But for now, again, we're trying to go for the simplest thing that could possibly work. Okay, now this is where we actually get to use the net package that we imported previously. Okay, and as I go through this, I may also show you I'm gonna link you to PKG. Go.dev, I believe. The go.dev. So what I'm gonna do, I think I should share my entire screen. That way when I switch between windows, you will actually see what I'm referencing. So let me reshare. I'm gonna share my entire screen. Great. So now when I switch in between these things, you'll see exactly what I'm doing. So whenever you're curious about a package, right, within Go that you'd like to sort of learn more about, if you head over to pkg.go.dev, right, and say we're importing the net package, I put net here, you're gonna see. Let me bump up the size. Right, you're going to get the list, sort of a listing of those packages that match. And this will index both sort of a standard library packages, but also third-party community packages as well. So again, you'll see the tag here that says standard library. That's a good indication that you are looking at a standard library package. So if I click on net here, you'll see that this package, right, handles, basically based on this description alone, handles everything relating to sort of your network I/O, right? It'll deal with your TCP/IP and UDP traffic and whatnot. So one of the sort of most commonly used functions in this package, right, is this dial function, right? So this is kind of the first step, right, of initiating that connection with that remote host. So remember when we're talking about, basically the definition of the port scanning thing earlier, we're going to be leveraging this very sort of fundamental function, right, from the net package to actually initiate a TCP connection to a given host. The host in this case happens to be my local host, but you can see here you can specify any sort of a DNS name or IP address that you'd like to use, right? But you also need to provide what the port is going to be. So if we go back to our code here, we see that the port we wanted to use was port 5000, right? So here we have this dial function, right? I mouse over and I get a nice sort of a little description here. Same exact documentation I was looking at before, because I have the Go extension installed in my VS Code here, and you can use your editor of choice. There's Golang from if you're familiar with the JetBrains suite of tools, you can get something from them. If you prefer to use Vim or Emacs or whatever, whichever editor you're comfortable with, there's typically an extension, a Go extension for those as well. That's going to give you some nice sort of a hints in documentation inline like this. Okay, so you can see basically we have different ways of actually invoking this dial function, but basically we're looking at the function signature here, whereby we see this sort of capitalized dial function, and I'll briefly mention also that Go doesn't do the concept of public and private, right? It does exported and unexported, which are kind of the same thing, just different words, right? Different terminology. But the idea is that basically in order to actually get to this dial function, the letter D, right, in that the name had to be capitalized. That's how Go knows which identifiers in your programs to export, to make available, right, outside of the package, package, in this case the net package, right? Which ones can be called. So other than that, right, if this was a lowercase, only other code within the net package would be able to actually call this function. And if you were curious and you want to navigate the net package's source code, you can do so on github.com/Golang. You can actually see the entire STEM library source code right on it's publicly available. You can read through it, right? You're going to see there's a lot of internal, right, functionality, as you'd expect, that is not exported, that is not made for public consumption by the developer, right? But you can still read it, right? But these exported functions are sort of the interface. They're the API for this particular package, right? So we're expecting the kind of network that we're going to be dealing with. Right? In our case, we're going to be dealing with TCP, but you can see there's a lot of options available for our interaction. And we need the address, right? This is where we specify the host and the port, okay? So, and we're going to get return, right? Two different values here. The first is going to be something that is of type netcon. Okay, and the next is going to be something that satisfies an error interface. So we may talk a little, touch a bit more on the error interface as we go, right? But the idea is that we can return all kinds of different errors if we choose custom errors, but also as long as whatever we're returning satisfies the error interface in Go, which is basically something that has an error method on it, right? It'll satisfy this particular interface. Okay, but for the sake of brevity and sort of getting through as much of this as we can. If you have questions about interfaces and how they work in Go, drop them in the chat, and John will be sure to bring them up. And also, if there'll be information to contact me afterwards or John afterwards as well, if you want more sort of a deeper dive on certain aspects that I won't have time to cover as we go through here. Okay, so back to the code. So what we're doing here, right, we specify our TCP as the type of network that we're going to need, and basically we string together, right, sort of this local host with a colon followed by sort of this marker for where our port is going to be. So basically we're saying, hey, I'm going to feed in this p value, right, p variable, into this %d, this format verb, right, to indicate that I'm putting in a digit here, right? And then basically I'm formatting the string so that at the end I'm going to have localhost colon 5000, okay? So when I call my dial function, I need to capture the return values, right? And I'm assigning the first return to con and the second to error. Okay, pretty simple, right? Simplest thing that could possibly work, right? And for our purposes, we know that whenever we get an error back, right, from the dial function invocation, right, regardless of why we got the error. Again, there could be a number of reasons. Maybe the host you're trying to talk to doesn't want to allow a connection. At some point, your dial connection will time out, right? And there will get returned from that. Maybe the host will allow the connection, but there is no process bound to that port, right? So there's nothing to listen to any sort of a traffic back and forth, right? Even if you get through a firewall, even if you get through the operating system and says, okay, yes, I will allow you to communicate, but there's nothing bound to that port, then you're going to get an error back from that, right? There could be a number of reasons why you get an error back. For our purposes, we're going to consider any kind of error that comes back to indicate as an indication that the port is closed, okay? But if we can somehow, right, manage to get to line 15, we're going to consider the port to be open, and we're actually using this con variable that we captured, right, from the net.call to actually close that connection because we're not doing anything with it. Remember, here we just want to probe. We just want to see, hey, is there something listening in that port? Right? We're not doing anything with it. We're not actually sending data over it, right? We just want to know, okay, can I actually establish this connection? Once we're able to actually establish that connection, we know the handshake was successful, then we know the port is open. And this is exactly what we print out here, which says, hey, that, we're going to consider that port to be open, okay? Simplest thing that could possibly work. Now, we haven't started the whole scanning thing yet. Scanning implies some sort of maybe you have a list you're going to iterate through. We're going to get to that. But this is right now just scanning a very specific port, right, on a very specific host, right, to see if we can actually, how does this actually work, right? So I'm going to open up my terminal here, and I'm going to do go run, and this is my first attempt, simplest thing that could work, main.go, okay? When I hit enter, hey, look at that. I see port 5000 to be, says that it's open, okay? That means I have something running port 5000 on my local machine here. So let's try something, perhaps that is, there is nothing running. Let's do run again, and we see that it's an error indication that again, we're treating any sort of error that comes back as as an indication that the port is closed, regardless of the reason, right? We can communicate on that port, so we're going to treat it as closed, okay? So I happen to know that I also have a Postgres server running, and Postgres typically runs on port 5432. If I were to change this, I run this program again, I should see that the port is open. There we go, that the port is open. See, so this is the simplest thing that can work. We know how to specify a host and a port, open a connection. If it succeeds, if the handshake succeeds, then we know the port is open. Otherwise, it is closed, okay? Simplest thing that could work. All right, now let's evolve this program a little bit. We want to do like an actual scan of a number of different ports, right? Not just one port, right? Hence the whole scanning that we've been talking about here. So all I'm doing, right, is here. The difference is I'm using the code, right, that I had before is the exact same, right? Same body, right? The only thing I've done now is wrap that inside of a loop, right? Go has one construct for doing loops, and that's the for keyword. Okay, Go doesn't do while loops. There's no do while. There's nothing like that. The one for keyword actually allows you to do all of these different kinds of looping mechanisms you might be familiar with from other programming languages, but Go only has 4. But again, you can do some of the same sort of fundamental basic initializing a variable, doing comparison and doing increment or decrement, same things you might be familiar with from other programming languages. You can do all that stuff here as well. Okay, so all we've done here is basically say, hey, I'm going to iterate over a couple hundred ports, right? And I'm going to be feeding in, right, whatever port number I have, right, with this variable I, which again I've initialized as part of my sort of a declaration here for my loop. Okay, again, simplest thing that can work. Let's open up our terminal and let's now run the sequential version of our program. We'll run. Here we go. Let's bump up to full screen here, and it's actually, yeah, we have the entire list here, and we've iterated from port 5300 over all the way down, and on the way down, hey, look at that. We found the one port that was open within that range, so we know our Postgres server is actually running on that host, and we've actually scanned all the ports and identified which one of them was open, and the fact that all the other ones were closed, right? So, John, we know that at this point we've seen how Go is sort of easily able to sort of handle this particular task for us, right? We've seen how the standard library, right, it was able to sort of provide the building blocks for building this kind of networked application, and we saw that we were able to sort of iterate through one at a time, right, through our list of ports, right, to see which one of them was open. Right, so is there? I'm thinking that this program could benefit from some concurrency, right? Because when we looked at our list, we went from the 54 or 5300, like one at a time through that entire list. Like, I'm thinking we can improve on this program somehow. What do you think?
Yeah, especially considering the fact that when you look at these, if we fail one port, it's not like it says something about the next port that's coming up. Mm-hmm. And I think that's usually a big sign when you're looking at concurrency is if the things need to be done sequentially, like one thing affects the next, then that's a little bit trickier to do. But if it's things that are all completely independent, then that makes it a great candidate for concurrency.
Right. And we have a name for these kinds of programs. We typically refer to them as embarrassingly parallel, right? There's no dependency from one task to the next, and that's usually your first indication, right, that this program might actually benefit from some concurrent execution, right? Again, this is so. The one sort of caveat I want to add to this is that sometimes doing things sequentially like this is just fine, right? Like in the case of our program here, we just wanted to scan a couple hundred ports, and if that's all you need to do, and the program executed fast enough, that's okay, right? You don't need to, just because the programming language provides some concurrency primitives and things you can sort of throw at it, you don't have to use that. Again, based on your needs, right? You may decide that, okay, doing it sequentially it works perfectly fine, and that is my default. Even as someone who's been using Go for many years, that is sort of my default. I implement my programs in a sort of a sequential, right, procedural way first, and then see, okay, well, where do I have an opportunity to increase performance or to utilize system system resources perhaps more effectively, right? I do the work first and then look for opportunities for optimization. So I'm I'm resisting the urge to jump straight to using the concurrency aspect of my code because I may not need to. All right.
This actually leads to a good question. One of the people in chat had asked, is there a way to prove the correctness of concurrent Go programs?
So this is, yep, go ahead. No.
I guess I was going to say that to me, like your thoughts on making it as simple and sequential as possible are like a great way of showing something that's working without introducing that complexity. Because once you start adding concurrency, things are a little bit trickier to find all the bugs, especially given that concurrent code can sometimes work and sometimes not, depending on how things are executed.
Mm-hmm. Yep, exactly. So one of the how do I put this? One of the ways I write production Go code is, again, to do it the procedural way first, right? Then when I add a concurrency to a program, I'm sort of doing it at the edges. So let me explain. So I may have a piece of functionality that if I'm exposing a behavior, right, to a developer to consume through a library or something like that, I'm not gonna force the concurrency, right, in my library. I leave it up to the developer who's at the edge, who's using my program to perform a particular action to control the concurrency. That way, when I'm building my library, right, unless I'm building something that is designed to be concurrent by default, right? Maybe I've abstracted away some queuing system or something like that, and I need to use concurrency to actually solve a particular solution, right? Most of the time, I basically create my program with the assumption that the developer is going to initiate, right, is going to use it in a concurrent way. They will fire off Go routines, and which we're going to talk about in a little bit. They will sort of orchestrate. They'll do all these things, and my program can be kept as simple as possible. My library can be kept as simple as possible, and I can write my unit test and without having to worry about concurrency or any of these things, right? I leave it up to the developer using my program to introduce the concurrency should they need it, okay? And we're going to see sort of how we're using concurrency, how we're introducing concurrency in our program as we go here, and hopefully that'll make a little bit more sense to those watching and to those who have similar questions. Let's share our screen again here and get back to some of that code. And let me do a quick time check to make sure we're on track here. All right. So let's go back to our code. Okay. So again, we've identified an embarrassingly parallel use case here. So what we're gonna do, right? We're gonna introduce concurrency, right, into our program here. So one of the ways to do concurrency, perhaps you've heard about all these things about Go routines and how Go makes it super simple to actually use, to create multi-threaded programs and things like that. And perhaps you come across the Go keyword, which basically is sort of that's our jump off point. That's sort of the primitive you go to, right? No pun intended, to start your concurrency journey, right? That's what kicks off all the magical things. Okay, so we've introduced the Go keyword here to actually spin off separate threads of execution, right, to actually do that scan. So we know scanning from 5200 to 5201, right, that there's no dependency between those things. So we're like, okay, these are good candidates for scanning. So I'm going to put a Go keyword, right, in front of an anonymous function here. And inside of my anonymous function block, right, I'm going to basically put in the same code I've been sort of using this whole time, right, to actually do the scan, right? The body, the core of the function hasn't changed at all. Right, and this is what I was talking about earlier, right? I might have a library to do port scanning, and inside of my library, when you call the scan function, right? Perhaps this is all I'm doing. I don't assume that you're going to want to do that concurrently, right? I'm not going to actually use Go routines in my library. I'm going to give you, right, the developer who's using my library to scan ports, right, the ability to you yourself, right, add your Go routine, right, to use my library within a concurrent manner, right? So this is sort of an example of what we're doing here, right? So what we're doing is we launch these separate threads of execution, right? And then basically we're just gonna, when we're done, when all the work is done, we're just gonna print done, okay? So now let's actually see how this works. So if I do Go run, and I do this one now, what happened here? Why is it done, like completely. Looks like we ran our program and we just jumped straight to line 21. John, what happened? Can you tell me what happened?
Well, it looks like either your code got really, really fast or it didn't do what you expected. So I think this is a common thing. When it comes to scheduling Go routines, if you don't actually know when they're going to exit and wait for that, there's no real guarantee that they actually get run, because when you call that Go func, you're just scheduling things. You're not actually waiting for them to complete. I mean, that's one of the benefits to concurrency, is that you can go do other stuff while you're waiting for it.
Mm-hmm, mm-hmm. Exactly. So if we don't control, right, if we don't take care of, and those who are familiar with the multi-thread programming from other programming languages are kind of, even they might not be familiar with Go here, but they might be like, okay, isn't there somewhere you need to sort of synchronize those things, and sort of maybe you spin up a separate thread, but you got to rejoin the main thread at some point, right? So that's exactly what's missing here. So what we've done, we've spun up, right, all these separate threads of execution, right? We've spun all these things up, and they're off doing the work. And then, when we did that, immediately after iterating through all these, basically iterating through all this firing off of all these separate threads, we just went straight to line 21, and we didn't wait. We didn't actually wait for this work to get done, right? We spin up all these threads, like hundreds of them, but we don't wait for the work to get done. And before we move on to how we actually fix this particular problem, this is a good place to actually talk about the difference between Go's threads, right? Go routines, right? And what you might consider or rather, in comparison to OS level threads, right? So what the Go runtime allows you to do, what the Go scheduler, right, allows you to do, is actually to multiplex, right, those Go routines on top of one OS thread, for example, right? So the Go runtime is actually gonna under the hood is gonna have multiple OS level threads, but those are kind of heavy, right? Those typically have a much larger footprint, right? So basically, and you don't want the Go doesn't let the operating system sort of dictate, right? When do threads get paused? When do each one? When does another one get resourced to execute, right? So the Go runtime sort of sits on top of those OS level threads and multiplexes multiple Go routines on top of each of those threads. So this is what allows you to have hundreds, even thousands of Go routines that still take advantage of very few threads at the OS level, because the Go runtime is managing that process and switching between them, right? It's basically it's the one determining when does each one of these Go routines, right, get scheduled to actually do some work. When do they get paused? When is control handed back to a different one? So the Go runtime is actually managing that for you. So that's why it's very, very efficient, and doesn't actually the OS level threads don't impact, right, at least to the same degree that it otherwise might be. It doesn't impact the execution of a program, right? Because the Go runtime is actually managing those threads for you. Okay. Now let's see how we actually solve this particular problem, right? Of actually waiting for these Go routines. And the way we do that is not through a sleeping function. we're not going to sleep on this. What we are going to do, however, is to synchronize, right, our execution, right? And this is where I'm also introducing some additional concepts as we go before we get to the synchronization process. So you saw me earlier creating some local variables, right, inside of this block here. So these variables are being created sort of locally inside my braces and my blocks. On this version of the program, you see I'm creating some globals here. So I have a host, I have a from port, I have a to port. Okay, I'm using these globals here, and I'm also introducing here the init function. Okay, the init function is a package level function. It's a function that is executed automatically for every package that you import into your program. So if you're wondering, that has a potential to have some side effects, well, yes. So that's why I typically recommend that if you are going to use an init function in your package, and again, this is for any package that gets imported. So for example, in these standard library packages, they could and often do have their own init functions. Every time you import the package, the moment your program starts running, every init function from each package is going to get executed. Okay? It's going to get executed automatically before your main function gets to actually happen. So when you run your program here, this init function is actually going to execute, and then your program actually starts, whatever's in your main function actually starts to execute. Okay, so this is one of the places where the Go community sort of has some idioms around sort of what you should use init functions for, because of the side effects that they have on your programs. Okay, in this case here, we're actually using the init function to do something that is sort of benign, right? Basically, what we're doing is basically we're gonna parameterize the invocation of our program so that we can specify the host, the port that we want to scan, and basically the from and to port, kind of specify a range, if you will, and just assign these things to these package globals, right? And then using those package globals inside of our other functions here. Okay, that's basically the new stuff we've introduced. And obviously here we're doing some checks to make sure that the range you're providing, right? Basically, I want to make sure that the from port is actually lower than the to port, et cetera, et cetera. So just do some checks here. Again, using the standard library. Standard library has a string conversion packages that I can use to check. So some typical things you might expect every standard library for a given programming language to contain. Okay, and you see how I'm handling my errors very specifically here, very explicitly. Go doesn't have the concept of exception handling. There's no try, catch, finally, none of those things. There is, however, basically the expectation that you will handle your errors just like you handle any other variable, just like you handle any other value within your program. So when I mouse over this A2I function, which is an ASCII to integer, if you will, you'll see that there are two values being returned. There is the integer that would have been converted, right, if your A2I call is successful, and then there's whatever satisfies the error interface coming back, right? So you must handle, right, this return and do with it whatever you want. If you want the program to end, like I do here, by firing off a fatal call and sort of executing, or rather stopping the execution of my program completely, right, and erroring out and crashing out, then I can do that, right? If you want to sort of put that in a log file, right, you can do that. You want to send that to some sort of external exception tracking tool, right? You can do that, right? It's up to you how you handle your errors, but Go expects you to handle your errors explicitly. There's no sort of an implicit sort of a bubbling of things and hiding of things and try and catch. There's no such sort of mechanisms in Go, okay? Now, let's move on to the part where we actually fix our synchronization issue, okay? So this is where we have sort of what's called a part of the standard library as well, what's called a wait group. The wait group is a construct to allow us to, as the name implies, wait on some Go routines, okay? So typically what we're going to need to do is we initialize our wait group, and we're going to need to know how many things am I going to wait on, okay? So to get that calculation here, remember, we're getting a to port and a from port, so we kind of know what range of ports, how many ports I'm going to need to scan here in this case. So I'm going to use the add function, right, in the wait group, and the add method, right, on the wait group I've initialized earlier to specify what the delta is, specify how many things I'm going to be waiting on, right? But when we add those things, right, and before we can actually wait on those Go routines, we actually need to decrement, right, so think of the wait group as a counter, basically, right? And when we tell the wait group to wait on our Go routines, right, which is what we do in line 54, right, this call, right, is a blocking call, meaning that your program will actually run through and actually for each iteration of the loop, fire off these Go routines, right? Same thing we were doing before, right? This code hasn't changed very much. We'll come back to this differ in a second here, but the same thing we were doing before, fire off these Go routines to do that work, right? And then once all these Go routines have been fired, your program gets to line 54 and is forced to wait, right? This is a blocking call. So how does this wait unlock? How does this wait allow our program to then continue to on line 55? Well, that's because this is where we actually need to sort of decrement, right, our counter. So remember, we're adding the number of things to wait on line 41, right? But we need to decrement these things as we go. And this is where this WG, right, this done method call on our wait group, this is where that comes in. So think of the done as a decrementer, right? It's going to decrement whatever value, whatever number we added with the add, we're going to keep decrementing, right, with the every time we call a done call, right? And we use the defer here, right? You're going to see defer all over Go code basis, right? It's sort of a kind of the one of the things that we rely on quite a bit to ensure, right, that a particular function or particular action or particular sort of a behavior gets run. Meaning that if for whatever reason an error were to get thrown here, right, even a fatal one, right, that this deferred call would get executed no matter what, right? So you can think of this loosely as sort of your finally, right, for languages that you might be familiar with that have that, right? It's sort of the thing that's the very last thing that before this function, this anonymous function here that we're triggering, it ensures that whatever happens inside of this function, this is going to get called. This means that come hell or high water, our wait group, right, will unlock, right, at some point, and our program will be able to sort of continue on to line 55. Okay, so this is the wait group. This is one of the sort of fundamental building blocks of actually writing concurrent Go code. Okay, and it's something I actually rely on quite a bit in sort of my day-to-day as well. So let's actually run this program. This is a synchronized.
After you run that, Johnny, I do have a question for you.
Yes, please. So I'm going to use the default, so the default parameters. So it's going to be, the host is going to be the local host, front port is going to be 8080, two ports going to be 8090, right? So when I execute this program, these are the defaults kicking in, okay? So here it is, the local host. This is a starting port and an ending port, okay? Now let's, and you can see, right, before we change the range here, you can see that this time around, right, unlike the first time we ran this program where we just went straight to done, right? You can see this one, we actually were forced to wait, right? Each one of these was handled by a separate Go routine. So we actually were forced to wait, right? This is the wait group in action. Basically, we have to wait for each one of those things to get done for us to know what the result was. Or was it a closed port, open port, that kind of thing, right? And we see how the wait group actually helps us ensure that we wait for all that work to get done before we actually get to the last line of our code for the done. Very different results, right? And this is sort of the way you'd synchronize, right? Those separate threads that you're spinning off, you bring them back into the main thread that fires them off, okay? What's your question?
So going back to the code, one of the questions that several people have asked is it safe to assume stuff in the standard library is safe to use concurrently? And if not, how do you sort of determine what can and can't be?
Right. So there, in the standard library, a lot of the things that are safe for concurrent access will be explicitly stated as such, and so will the things that are not safe for concurrent access. For example, maps in Go are not safe for concurrent access. So you need to use things such as mutex, right, to sort of guard access to those things where multiple Go routines are involved, right? If you have only if you have again, if we go back to the sort of the first sequential operation. Or version of this program that we ran, if we're using a map somewhere in there to keep track of ports that we were scanning, and in that case, because we don't have multiple Go routines accessing that map, it would be safe to use, right, without that mutual exclusion. But if you have multiple Go routines accessing, things like a map, right, you need to sort of guard against multiple Go routines writing at the same time. In some cases, it's okay to read, right, and which is why we have a different locking mechanisms. We have locking mechanisms that are exclusive entirely both to reads and to writes, and we have those that are exclusive to writes, but they are open for multiple reads, right? So depending on what your use case, what you need, right, a lot of the standard library code will actually, the documentation will tell you what's safe for concurrent access and what is not. Okay, all right. So I promised you that we would see, or rather, let's change. Right, let's actually modify the default a little bit. Let's add the 2 port. Let's change the from and the to, right? And let me do a quick time check here. Okay, go, still good. To actually see our program in action. So let's say from, and we'll say this is a 5,000. Let's do 5,200, and let's override the 2, and and that is going to be, say, 5,500. We run that, here we go, and we should have found the port that is open, There we go. Here's the port that is open, 5432. But notice that this time around, there's no sequential. This is not a sequential scanning operation going on here. You see the from 5231 to 5429 to 5297. You can see the each go routine, right, actually gets to do its work, right, sort of not in sequence with the other ones, right. This is exactly the behavior that we're looking for. We're allowing the scheduler, right, to determine when each go routine is ready to go and to perform its action, and all of this work happens concurrently. Okay, now the next example we're going to look at, right, and this will be the sort of the final example before we actually before I start pointing you to some additional resources, right, is going to be the concept of a worker pool, right? So what we're going to do, right, we're going to see why in certain cases too much concurrency can actually be a problem, right? So before I do that, right, so what I'm going to do now is actually I'm going to change the how many ports I'm scanning here from something small, right, like say port 80, right, to something very, very large, right? So remember our code. Let's take a look at our code again. Let's bring up our synchronized version of our code. Although this version of the program is much safer, right, than or rather much more performant, I should say, much more concurrent than the previous one, right? It is not necessarily safe because there's nothing here to prevent you from sort of running afoul of the operating system, right? Because what we're doing here, we're basically saying, hey, how many go routines do I need to launch? And then I go and launch all of them, right? So if I said I wanted to scan thousands of ports, that means for each one of these ports that I want to scan, I'm going to be launching thousands of or rather, I'm going to be launching a go routine, meaning that I could potentially have thousands of go routines running at the same time. Okay. Now let's see how that could run afoul of the operating system. So say I want to scan, right, starting from port 80 to port 65,000, right? So if we do the math here, I'm going to have a lot of go routines running. So let's see what happens when I actually run this. I think I prematurely ended the execution of the program. All right, there you go. I think we saw some of the bad things that happen when you have too much concurrency. So you see, as we were iterating, right, through our scanning process, some of these things were behaving as we had intended, but we also ran afoul of the operating system here, because what started to happen is that the OS started to tell our executing program that, hey, buddy, I know you're trying to get a lot of things going here, but you actually have too many file handles open, right? This is our operating system guarding itself from our program, which is sort of going haywire and spinning up a lot of different go routines. And the OS doesn't care that you're using go routines, or doesn't care what your program is doing to actually run afoul of the limit, right, it has on how many file handles any one process can have open. It just knows that your program has run afoul of that limit. So this is where, when you're writing concurrent programs in Go, or really in any other programming language that support concurrency, is to be careful of the context in which you are actually running these things, right? So in this case, it's the OS saying, hey, I have a limit on the number of file handles you can have open, right? And you've exceeded it. In other cases, it could be maybe you have a database connection pool that you've exhausted the number of connections in that pool. In other places, it could be that you're interacting with a remote HTTP web service, and you're getting throttled with 429 response codes back, right? Regardless of the system constraints, or regardless of what the problem domain you're in, right? You have to make sure that your concurrent code, right, however beautiful and well crafted it is, that is not running afoul of the constraints of whatever system you are actually interacting with. Okay, so in a large majority of cases, Go is not your bottleneck. Go's concurrency capabilities are not your bottleneck. It's going to be the network. It's going to be the disk. It's going to be the CPU. It's going to be the boundaries, right, that those systems that you're interacting with have set for themselves to protect themselves from being flooded with requests. Those are going to be the things that you need to worry about. So how do we solve our local problem here? How do we solve the issue with our operating system telling us that we have way too many file handles open? This is an unbounded concurrency problem. How do we bound our concurrency? How do we ensure that we don't run afoul of this OS level by basically controlling the number of Go routines we have open at any given time? Okay, this is where this next example comes in. This is where we introduce the concept of a worker pool. Now, for those who don't know, the worker pool basically says, okay, I'm going to have a set number of workers. In this case, our workers are going to be our Go routines, and we're going to have a set number of them, and they're going to be, that set number is going to be in charge of doing the sort of the work. We're going to have we're going to have to feed those workers a job, and once we've reached the total number or the maximum number of workers our program, right, is allowed to have, right, we're just going to basically wait for the next available worker to be free, right, to pick up the next item in the queue, so to speak, right, and to start actually doing that work. Okay, so we're controlling the number of Go routines we can have active at any one time, and hopefully find a way to mitigate our problem with the system that we're sort of dealing with, which in this case is the operating system preventing us from having too many file handles open. Okay, so in this case here, to determine the number of workers, and again, there's no exact science, right, to determining the number of workers you can have for your program, right? It depends on the system that your program is going to be running in. It depends on the things that you're actually interacting with, right? But in my case here, I'm actually using the runtime package. The runtime is also part of the standard library, right? So it's imported here on line 10, right? I'm using the runtime package, and it's able to tell me, the num CPU function is able to tell me, hey, how many logical CPUs does this particular machine have? Right. In my case here, I think the machine I'm on right now maybe has 12 or something like that. So that's a good place to start usually. For me, I typically don't know, right, until I've done some benchmarking, until I talk to the rest of my team and says, hey, what kind of system resources are we going to be expecting, to have in production or stuff like that, right? Are those sort of beefy machines with lots of CPU horsepower and lots of memory, or like what kind of workload am I dealing with? Is it CPU bound? Is it memory bound? Where are my constraints, right? And then basically we find out what the sweet spot should be, right, if we are using this particular pattern, right, to solve our work. In this case, I'm using the num CPU because it's a good starting point and it works for what we're trying to do here. Okay, so that's our default. But we can override that again through by parameterizing it. We can override that so that when we invoke our program, we can change the number of workers that we want our program to run with. Okay, so here we've introduced yet another concept. Basically, we're just going to have a slice of integers where we're going to keep track of our open ports, right? So every time we do a scan, if the port was we found the port to be open, okay, we're gonna add it to this slice, right? And for those who don't know, a slice is an abstraction on top of an array, right? Because arrays typically need to have a sort of a set size, right? And if you need more things to go in the array, you have to create another larger array, copy the things from the previous array into the larger array, and then leaving room for whatever else you want to add in there. So the slice is actually going to take care of all that sort of a moving of the bits around for you under the hood. Okay, so you don't have to actually do that yourself. So that's sort of the primary benefit of using a slice. Okay. And basically here, I'm also basically introducing some signal handling, because what I want to do is to basically, regardless of where I'm at in the processing of the ports, say I'm processing a large number of ports, and when I hit my Control C, when I signal the termination, right, for the program, I want to trap that and make sure my program doesn't just end abruptly, right? I'm just going to trap that, and basically I'm going to print out the results I've gotten so far, right? And then I'm going to use the OS package to exit out of my program cleanly. Okay, so this is a very common practice for sort of tools like this. Okay, you don't want to lose, or basically you want to sometimes you want to end or shut down your program cleanly, and this is a very common pattern for actually doing so. All right, so next up, we've abstracted away our parsing of the ports, right? All that stuff I was doing with checking that you give me a good bound for the ports, make sure you don't give me letters instead of numbers, etc., etc. I've tucked that away into this little helper function, which is just going to give me back a slice of integers for the ports that I need to scan, and something that satisfies my error value. Okay, and basically I'm handling my error. I'm basically saying, hey, if for whatever reason I give you bad input, I'm gonna nicely tell you that you need to give me something better and actually end the program with basically cleanly. Okay, and then now this is where things get interesting. Okay, this is where we get to use the Go's concept of a channel. Okay, so channels facilitate communication between Go routines. Okay, there's a couple of ways this communication can happen. Okay, the first is basically by having what's called an unbuffered channel. An unbuffered channel means that I have a pipe that I'm going to send, one Go routine is going to send a value on one end of the pipe, okay? And another Go routine, right, is actually going to consume the same value that I'm sending on the other end of the pipe, okay? In an unbuffered scenario, whereby, meaning that only one value can travel through that pipe at any given time, right? If I don't have something on the other end, if I don't have another Go routine on the other end to read values off of that, out of that pipe, then this is going to be a blocking operation. So I'm just going to be sitting there waiting to send something in, and until something on the other side is ready to sort of pick up that value that I'm sending, right? I'm going to have a blocking operation. So sometimes I may not want that. Sometimes I do want that, but sometimes I don't want that. So this is where I have the option, right, to have a buffered channel. In a buffered channel, it means that I can send up to the n number of whatever whatever buffer size is. I can send up to n values in that, right? So if I have multiple Go routines, each of them wants to send a value on a buffered channel, right? The Go routine one comes in, puts in his value, moves along, goes and does something else. Another Go routine comes in. If it can feed something into the buffer channel, right? If the channel is not at capacity, it gets to put something in and goes about its business. But if another one comes in and says, "Oh, I don't know, the channel's full," nothing has picked up, right? Nothing has picked up. No other Go routines have picked up things on the other end, right? That new Go routine trying to put something in that channel is actually going to block. It's going to wait there until, right, something is able to pick up on the other end of the channel. Okay, let's actually, and I'm actually creating both of them, both kinds of channels here by creating a ports. This is where I'm going to feed the ports that I need to be sent, and I'm using the number of workers here as sort of the size of my buffered channel. Okay, this is, remember, I want to control the number of ports that I'm scanning at any given time. So that's why I'm creating a buffer channel here of integers, where I'm, my port numbers are going to be integers. I'm creating a buffer channel here to actually up to the number of workers that I have working, right? And once I reach that limit, that means I cannot put anything else into the ports chain, meaning that basically that's going to be a blocking operation, preventing my program from running haywire and creating tons and tons and tons of Go routines to actually read and actually do this work. I'm creating sort of a natural limiter here based on the number of workers that I have, right, to actually do the port scan. And for the results chain, basically, I'm handing that results chain over to my Go routines so that when they're done with the scanning, they have a place to put those results, right? And here, I'm basically going over the number of ports that I need to scan, okay? And actually spinning off a worker, right? Passing in, hey, this is the host that I'm going to be using. It's the same host for every one of them. But the interesting bits here is that I have a ports chain and a results chain that I'm passing in. So let's actually see what the code for this worker looks like. Whoops. Actually jump to, there you go. So this is what the function looks like, okay? So the interesting bits here is that I have a ports chain, which is going to be a read-only integer channel, right? This is what this left arrow on the left side of the chain is actually telling me. This I can only read, right, from this channel, right? So this is where my ports to scan are going to come in from. This is where I get to read from, from that channel and for the things that I need to scan, right? And then I also receive a results chain, which is because the arrow now, right, is on the right side of this chain, meaning I can only, as the Go routine, I can only send on this channel, right? So I'm reading from the ports for the ports chain for the ports that I get to scan, and when I'm done, I'm sending, right, a result back on this results chain. And inside of here, I'm using the range keyword to actually read from the ports chain. So you can actually use the range keyword, part of our for keyword, sort of set, right, to basically allow us to read values from this ports chain. Remember, we're going to be feeding ports into this ports chain. So as long as they keep coming, I'm going to keep reading, right, from this ports chain. Okay, and again here, same basic thing we were doing before, right? A slight modification to allow us to basically whenever we find a port that's closed, we just move on to the next thing, right? With this continue keyword, right? But basically doing the same thing we're doing before, using the net.dal, determining whether the port is closed or not. If it is closed, we send a 0 into the results chain because we don't care about that port number. Otherwise, if we can get to 111, we're not doing anything with the connection. We close it and we just send that port that we found, right? We send that result onto the results chain, right? So if you think of sort of this as almost like a sort of a pipeline, right? You can kind of see sort of the flow of that data. So all we need to do at this point is to basically say, okay, well, I need to actually feed ports into this ports chain. Because the moment I do, this for loop is actually going to start reading ports of that channel, right? I'm going to be doing the work, and I'm going to be, either sending in a 0 to indicate that I couldn't open the port, or sending a speed to say, hey, yes, I did find the port to be open, and here's what it is. Okay, let's scroll back up to where we actually feed this ports chain. So in this case here, we're spinning up a separate Go routine and ranging over the ports to scan. Remember, this ports to scan came from basically determining what the list that I gave, the range that I'm specifying, right? That's a slice of integers. I'm going to be ranging over, right? That slice of integers, feeding in ports, right? And basically, I'm going to be able to feed up to the total capacity, right, for the ports chain. Meaning that ports chain, remember here, the capacity for it is up to the number of workers that I can have working on those port scans at any given time. So this, when I'm launching this when I'm feeding in the ports, at the moment I run out of workers to actually pick up this work, this is actually going to be a blocking call, right? So when I try to feed P into the ports chain, that's going to block. If I have 12 workers active, right, on the 13th one, right, this is going to be a blocking call, right? But the thing is, we don't want this code here, right, in our main Go routine to actually block the rest of our program, which actually needs to happen down here, right? We don't want that blocking operation here in line 55 to actually prevent the rest of the program from running. That's why we put it in its own Go routine. Okay, let me repeat that. That's one of those subtle things that you kind of need to sort of you worry about when you start writing these concurrent programs, right? So I need to feed in, right, n number of ports, right, into this ports chain. Remember, it's a buffered channel, but the moment I've run out of buffer, the moment I've run out of room to put in values, this is going to be a blocking call. 55 is going to be a blocking call. If I don't have, right, if I don't put this in a Go routine, my program is going to execute, and it's going to stop right here until more room gets created. None of this is actually going to get executed, meaning that as my Go routines, right, do the work here where I'm actually reading those values off of the results chain, I'll never be able to pull results of the results chain because I never got to this part of the code, right? So I don't want this line 55 to block my Go routine, my main Go routine, my main thread. I don't want that here because I want this part of the code to execute, right? And I still need to feed ports into this ports chain. So I'm going to create that in a separate thread of execution, right? So that when this call blocks, it blocks just this Go routine, not the rest of my program, okay? So the rest of my program, then I'm able to sort of read right off of the results chain because I have this sort of a left arrow here, right, coming off of results chain. So as results get put in by these different Go routines, right, I'm able to assign the result to P. I append, right? Remember open ports that we declared earlier. I append a value to that open ports, and then I'm able to actually, I close those channels because I'm no longer going to be feeding any values or reading any values from them, and I print out my results. Okay, so I know there's a lot of moving parts in here, right? But let's actually see it in action to see if it solves our problem. Remember, we tried to scan 80 to 65,000 earlier, and things blew up because we ran afoul of the operating system, right? So let's actually see. Let's make sure. Okay, let me see. This is using ports, a slightly different version. So let's try. Let's do go run, and let's do. This is the. Nope. This is the worker pool. Main.go. All right. So if we run this, okay, so this is using the default parameter. So from 5400 to 5500, right? That's the default ports that we just scanned. So basically here, It just basically says, hey, I've just scanned, right, this handful of ports. All right. So now let's execute the program again. This time, let's say ports. Remember, we were passing 80 to 65,000, the very large port range that sort of we ran afoul of. Let's actually see if we can how this works now. You see, at this point, our program is running, right, and we're not seeing the same problems we saw before, right? We're seeing expected results. We're seeing basically, hey, that the connections are refused, but nowhere do we see the operating system saying, hey, you ran afoul of you have too many files open. Right, so we're able to constrain, and I'm going to hit Control C here, right? When I hit Control C, and this is we see our trapping mechanism comes in, I'm able to print the results. I could see that 5,000 was open, 5432. That's where my Postgres is running, and I have a couple of other ports that I'm very suspect of. I'm like, what are the? I don't recognize those ports, so I'm going to have to look at what those are after this presentation. But I was able to sort of basically control, right, the number of workers I have in my worker pool, the number of workers actually doing the scanning process. So I was able to constrain my Go routines. I was able to bound them to prevent my program from running haywire and violating the system constraints under which I'm working. Okay, so there is a lot here to cover, and we haven't even gone through all the other patterns, and I haven't touched on semaphores. I haven't touched on how do you do timeouts, what happens if you don't care about certain results anymore. There's the pipeline pattern, there's fin outs and fin ins with workers. I mean, there's a lot here to cover, and obviously, we don't have that kind of time to go through all of these examples, but you have access to the repository, right? You can go through these things. If you have questions, please do not hesitate to reach out to me, on Twitter or LinkedIn or wherever you're comfortable, right? And even John is happy to help you. John does this for a living. He teaches this stuff for a living. I teach this stuff. So we absolutely welcome and encourage you to reach out to us if there's something that doesn't quite make sense. We are more than happy to help you on your journey. And one of the things I will mention, and I promised you that I would point you to where you go next, right, on your learning journey. Again, this is the repository, right, you have access to, okay, that you can go through the rest of the examples that we didn't get a chance to, right, and, right, in the README, right, if you're new to Go and you really want to get more into Go and need a sort of a prescriptive starting point, check out the README, right. I'll tell you exactly where to go, what you're going to get out of it, right, what material do you need to sort of look at next, and what sequence, right? Do the Go tour, read Effective Go, right? And then, basically build something. I even give you some ideas on projects, small little projects you could build to help you along your journey. These are the kinds of things that are going to build up basically your sort of your ability to write Go code. And you can actually use some of the patterns that I have in this repo, actually, right? And basically sort of the next steps in terms of how do you write Go code like Go developers do, right? And the resources there, and other links to sort of where to go next to find more documentation, maybe read the spec, or get some tutorials and whatnot. So if you're curious about how to go about it, what next, how do I beef up incrementally in Go, this should be a good starting point for you. And hopefully it's useful. And again, don't hesitate to reach out to myself or John if you come into any sort of blockers. This is all the time we have, John. This stuff is so much. It's just so exciting, but we only have so much time.
Yeah, and there's definitely a lot of questions we didn't get to, and as Johnny said, if you reach out or ask, this code base. I've looked at all the code Johnny has in the port scan package, and we're both happy to try to answer some questions and help people understand that a little bit better.
Indeed. Okay.
So since we don't have time for more questions, I'm afraid we've run out of time. Johnny, thank you for this informative presentation. The talk and all of your answers were very insightful and helpful. And thank you for everything else you do for the Go community. There's also a survey that is going to be presented after this talk. So if you have a chance, please fill out the survey. The talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements and other upcoming talks and things like that at learning.acm.org or acm.org. And as I mentioned, please do fill out the survey because it helps us figure out what future topics or future speakers and other things like that can help improve these talks. So on behalf of the ACM, Johnny Boursiquot, and myself, Thank you again for joining us. I hope you will join us again in the future. And that concludes the talk.
Bye.